To bring quantum dots to technical applications and everyday applications like we see them today, a method was required that would enable the production or the manufacturing of quantum dots with very high quality and in a scale, in a way that allowed it upscaling into industrial scale. Such a method was invented by Professor Moungi Bawendi, who is a native of France, received his PhD in 1988 from the University of Chicago and is today a professor at MIT. Please welcome Professor Moungi Bawendi for his Nobel Prize lecture.
I want to start by thanking the Royal Swedish Academy of Sciences and the Nobel Committee for Chemistry and the Nobel Foundation for this incredible honor of being here in front of you. As was explained in the last two talks, quantum confinement is key to understanding the properties of these semiconductor nanoparticles, these quantum dots. And what you see here on the screen is a series of vials of different sizes dots that are emitting at different light frequencies. And at a basic level, you can think of quantum mechanics being the important property that the electrons acquire at this small size scale. When you think of an electron in a circuit, you think of a small particle moving around with a velocity, etc. When you try to stuff an electron in a small box, like a small nanoparticle, that electron can no longer be described as a little piece, as a little particle moving in the circuit. It can only be described through the laws of quantum mechanics. It becomes a wave. And as you know, when you have a wave in a, for instance, in an organ pipe or in a flute, that the size of the wave depends on the boundary. So a small organ pipe has a smaller wave in it, a sound wave, than a big organ pipe. And it's that effective idea that happens here with the electron and the quantum dot. And that change in the wavelength of the electron eventually gets translated in a change in the wavelength of the light that is emitted by the particles. So the red particles have a longer wavelength and the small particles have a shorter wavelength. I want to start off with my timeline from my time at Bell Labs to my time at MIT, where we ended up creating this synthesis that is recognized by the Nobel Prize Committee in 1993. I want to thank especially the students that were with me at the time, Chris Murray, David Norris, Manoj Nirmal. It took an adventurous group to join a young assistant professor on his journey at the time. So let me start with the Bell Labs prep that Lewis talked about, what I will call the phosphine prep. At the end of 1989, I was a postdoc, and I stumbled into that. The phosphine prep, and I have my slides also from 1990, etc., on transparencies. The micelle prep, it should be called the inverse micelle prep. Steigerwald, Alvasados, and Brus developed that before I came as a postdoc, basically creating little droplets of water and making the reaction at room temperature in these droplets of water to eventually create a small powder of particles. And what they had found that by annealing the particles at, for instance, in a Lewis space like 4-ethylpyridine at 160 degrees, you could make better particles. The water amount regulated the particle size. So what they had found that by boiling in pyridine, these particles, sometimes they found this very interesting transition, this very sharp peak in the optical spectrum around 410 nanometers. And my job was to try to figure out what was that. And I really didn't know any chemistry. And really, Mike Steigerwald, who is here today, taught me everything I know about organometallic chemistry. I was a theorist first, and then I became a spectroscopist. And then, through an accident of time and space, I ended up at Bell Labs working with Lewis, who really taught me how to be a scientist. So I didn't know what a Lewis space was, so I asked Mike, what is a Lewis space? And Mike showed me a bunch of Lewis spaces in his lab, so I took a bunch of these things, and I started cooking the particles and whatever I could find. And for most of them, nothing much happened, but there happened to be a bottle of tributylphosphine where some magic happened. And you can see the word magic on this slide. You don't see that very often in a scientific talk. It was because we really didn't understand much what was going on. But what we found was that these particles grew and changed color. And at the end of the process, we obtained this amazing sample, much better than we had seen before. And I wrote a paper on this called the X-ray structural characterization of larger cat-selenide particles, and this is the experimental section. And you see underlined in red the words occasionally. That was part of the magic. So occasionally a red color appeared. What we had created was a material that had a much better crystalline structure than before. The optical properties was much better. So as you go down the side here, you see this very broad-looking thing on top. And as you go and anneal at higher temperatures, eventually coming to this phosphine prep, you start seeing the appearance of structure in the spectrum. That showed that the particles were getting better. We did X-ray analysis, and the width of the peaks that you see on top are an indication of the coherent size of the crystal that's in it. So broad peaks means that the material is mostly amorphous, and sharper peaks means that it's more crystalline. And so as you see that, as you anneal at higher temperature, the crystallinity also increased. Going to low temperature is also something that we do quite a bit. This is at 15 Kelvin, because at room temperature, your analysis of what's going on is hampered by thermal noise. Things get broadened out by thermal noise, which you can eliminate by going to low temperature. And what we found was this sharpening of the spectrum, indicating that we could now see really the size distribution was getting much narrower, and we could really see this wave, the electron wave, this exciton, being very well defined in the particles. And most importantly, in the lower left-hand side here, you see by combining this really beautiful sample with an optical method which selects the biggest particles in the sample, we could see the very sharp structure of vibrations of the atoms inside the particle. That showed us that we had finally found something that was really quite crystalline, of the quality that we were after. But the problem is that I could only make one size. And if you're trying to understand the size evolution of material from molecules to the bulk, and you've only got one size, you don't really have what you need. And so that's when I come to MIT. We tried to reproduce this with Chris Murray and David Norris, taking little seeds of these water-based materials and growing them in the phosphine, and quickly realized that this irreproducibility was a huge problem. The lack of size was a huge problem. And within a few months, Chris Murray and I, thinking about the nucleation and growth of making crystals back in the 1950s, which is what I had been using when taking little seeds that were water-based and dissolving them and growing them further. So we got rid of all the water-based part, and we switched completely entirely to organic, air-free based organometallic chemistry. And instead of making little seeds in water, we developed a process called the hot injection method, which is what people call it now, where we introduced and this is a picture of Chris and David from that time here. We introduced the precursors rapidly through a syringe here into a hot solvent that contains the surface molecules that slow down the growth and provide a uniform surface of the particles. Okay, once we did that, that was all good, but still the quality wasn't good enough. You could tell from the optical spectrum that these peaks that we were looking for were not getting sharp enough. The distributions were still within maybe a bigger than 10% distribution, and my goal was nearly defect-free particles, a size series, a consistent surface chemistry, and especially a narrow size distribution. Because we really wanted to study the physics of this evolution. And without a sample, we didn't have anything, and it was kind of scary at the beginning. You know, I start off, I want to do all these experiments, and I need a sample, right? We need our samples, and so that was really the issue, the necessity of the samples, which drove us towards working very hard, towards Chris and David and I to work very hard to figure out how to do this. And Chris was working in the lab, and David was, you know, getting his physics experiment ready. So as was Manoj Nimal, the third student of my initial group, and also these initial molecules we were using were very expensive. They were little bottles, and they were costing hundreds of dollars a piece. We were running through that really quickly. And we realized then that you know, the temperature needed to be higher, perhaps, and we needed something cheaper. And so we found this octyl-based tributylphosphine octyl, which is a longer chain, which has a higher boiling point, which happens to be used in the mining of uranium. So it's made in the train load. It's super cheap, and so that was great. And so it had the advantage of having a higher temperature, at much higher, 300 degrees or higher. And as a result, when we switched, we were able to get bigger sizes, get our size series, and then finally, adding to that, because we're chemists, we think that at the end of the process, we have to purify our material, and ended up having what we call size selective purification. This is a slide from that period also. Now I have a laser printer, so it's not all handwritten. Crystallinity, high temperature, uniform surface, all the same molecule. The idea of Lemaire from the 1950s of separating the nucleation and growth, as Aleksey was talking about. You nucleate little seeds and you grow on the top of them to get uniform size distribution, and you end up with uniform particles, which you can extract with solvents. I have a video here of what the process actually looks like. So there's the syringe here. There's the flask, which is at around 300 degrees Celsius or so. And the injection, followed by the nucleation, immediate change in color. And now we're gonna have a gap in the time here because we don't want to spend 3 hours here waiting for the particles to grow. The student here is taking samples out, and you can see the color changing as he takes the samples out. So we've had a gap in the time now. The color is much deeper red. There are much bigger particles, and you can see now the change in color as the particles grow from orange to red, and let me speed it up to the end here. And then when you shine UV light on them, you can see that they're emitting at different colors. So we have our size series. And we wrote this paper, this 93 paper that is cited by the Nobel Committee. It was a simple route. It was scalable, and that was important for the future, for manufacturability. It gave us high quality. It had a consistent crystal structure. It was a single step process. And if you're thinking about manufacturing, the cost of manufacturing is basically scaled by the number of steps that you need to make. So this was quite important. And then the last part with the purification, this size selective precipitation, which by taking a bad solvent or a poor solvent into the solution, the biggest particles have the strongest attraction. They will come out of the solution first, and you can get rid of those. And so you cut off the tail here. You're left with a solution that has where the bigger particles are taken out. You can do it again and take out the small particles, and are left with a very, very narrow size distribution. And you can see the result of that in TEM here. Electron microscope, transmission electron microscope image. You can see that they're really all the same size. This is from that paper here. You do the X-ray analysis. The solid line is the theoretical expectation for a particle of that size as a pure crystal, and we see that we match theory quite well. And now we have this beautiful absorption spectrum. So this peak here, that was that first. This is basically the electron wave filling up the particle, and then the other peaks you can think of are harmonics. You know, like in music, you can hear the harmonics of the different scales. So these are basically harmonics of that waves here. So that was the first indication that we could see the excited harmonics of the particle, and the emission was now extremely narrow. much narrower than before, right at the edge here, and much brighter than before, around 20% or 30%, what we call the quantum yield, which is the ratio of the photons that come out to the ratio to the photons that we put into the material. 100% is the best that you can do. And the exquisite tunability that Chris Murray was able to do with this synthesis here is shown here. So this is a psi series, and you can see the change in the color. This is 400 nanometers is blue, 700 is quite red, and you see the change in color. So the difference between any of these two is basically a handful of atoms that give you this huge change. And then as you look at a blow up of a few of the ones on my left here, you can see these harmonics being shown very nicely. Okay, so this is where David comes in now with his physics experiment, because now we're ready to really understand this evolution. And the first thing that you do is you go to low temperature again, and then you incorporate optical experiments where you can select even further the sizes of the particles to study them. And whereas at room temperature here, you can see the harmonics sort of spreading out as you get to higher and higher pitch. When you actually do the experiments, you see that it's more complicated than that. And the reason it's more complicated is because these are not empty boxes. These are boxes that have atoms in them. And that electron wave interacts with those atoms. And so you see interesting things like, you see that the harmonics here wants to go get higher pitched, but then it gets repelled by another harmonic here. In spectroscopy, we call that an avoided crossing. And when spectroscopists or physicists see avoided crossing, their hearts swoon, because this is what we live for sometimes, right? And so this means that we are really studying the physics of the material, not the physics of an amorphous material or the physics of defects. Because when you start in this field, you're always worried, am I really studying the real thing or just defects? And nobody really wants to study defects at this stage. Manoj, pictured here, was ready to do magnetic experiments. And the theorist, Sasha Efros, who's here as well, who guided us through this period with his intuition. And the theorist predicted that the emission from the light that would come out would be what's called forbidden, meaning that it would take a very long time for that electron to go back to the ground state to find its home. And so the light would take a long time to come out of the particles, but in the presence of a magnetic field, the magnetic field would shorten that time. And that's exactly what we found here. This is time on this axis. This is the amount of time that the light comes out. With the field off, it's longer than with the field on. That was another indication that what we were really studying was the real physics, and that our samples had gotten as good as we could make them, and certainly well enough to study the physics. Okay, now you've got these beautiful particles, and they behave a little bit like artificial atoms. You know, you create these electrons, and they're waves, the waves that you can change the size. And what we had found initially in these initial pictures was that they tended to want to assemble in a well-defined manner. And it turns out that if you're very careful, you can essentially create supercrystals out of them. You can create supercrystals of artificial atoms. And this is an image from a paper by Sherry Kagan, Chris Murray, and myself, showing the beginning of the assembly process here, or this is now a field that has taken off. He is creating interesting crystals out of these supercrystals out of artificial atoms like this. And in an SEM, surface electron microscope, you can see the individual dots here assembling into these bigger and bigger crystals, eventually making macroscopic crystal. And this is the picture of Sherry from the early 90s working on this. And so when you do that, then suddenly you think about, okay, maybe we can give really new and interesting properties to these crystals of artificial atoms. You know, the normal crystals made out of normal atoms look nothing like the atoms they're made up with. You can make semiconductors, you can make metals, you can look at transport properties. And so this is what we were thinking about. You know, how can we now use these particles as a new periodic table and make new materials? And There's a huge field working on that now, and Sherry and Chris are still working on this area now with beautiful, beautiful results. Okay, I want now to spend, okay, this is a picture from 1998 that shows the characters of the story. There's Sherry, there's Chris, there's David Norris, there's myself, Sasha Afros, a theorist, Tim Harris, who was at Bellas at the time, who will come in my story very briefly in a minute, and Manoj Nirmal on the side here. Okay, a big improvement, a step towards the commercialization of the material was this realizing that that you could keep adding new materials on the surface of these growing particles. And there was a series of papers in the mid-1990s. Margaret Hines and Philippe Guillaume showed us that you could get quantum yields as high as 50%. So there was an improvement of what we did, better stability, and a bunch of us worked in that areas at the same time, giving us these beautiful colored vials, emissive. And when you have tunable colors that are bright, that can all be created using a simple blue light, you start to think, how can I use this thing for? This is kind of an amazing new material. What can I do? What can I do with it? And this is where the application started. The first use for them was not a real commercial application. It was the realization that these things were now very stable and good enough that we can actually see them one at a time. And when you see them one at a time, you discovered a wonderful new world. For instance, you discovered that these things are like stars. They blink on and off, and we have to try to understand that. You discover that you can actually go and look at the spectrum, look at of these materials, and you see that as you cool down, that they're all different. They all have different spectra, but they're very, very narrow. You can see that here on the scale here, and that has. Then you look at the dynamics. You see all sorts of new dynamics that you didn't expect. This is the exploration of science. You find a new material and you do experiments. You find things you didn't expect. So we saw this is energy on the scale as a function of time. You see jumps. So basically, these little particles become sensors of their environment. They're not isolated. They live in a matrix where there are electrons that are moving around, the electric fields that are moving around, and so all these jumps that we see are due to charging or of the particle itself, charging of the surface, or local charge dynamics. Eventually, we figured out how to make the particles so that they were less sensor of the environment, more stable. And recently, that has allowed us to apply these materials, or begin to apply them in quantum optics. And what you see here is a recent result showing what is called two-photon coalescence. So if you can get photons coming from these particles that are indistinguishable, that look alike in every possible way, and you put them on a beam splitter here, one coming from the bottom, one coming from the right, from the left here, instead of coming out in stochastic way, they will always come out together. And this coalescence is a hallmark of what we need, what is important towards making a quantum communication and quantum computers optically. I talked about particles as building blocks. I want to show you one example of super nanoparticles. This is combining quantum dots here, semiconductors, with magnetic particles to create these superparticles now that are even bigger. So this is the building block idea. These superparticles are made up of luminescent quantum dots and magnetic little particles, and so they react to a magnetic field by being attracted to it. So they're both emissive and magnetic. They end up being these little core shells where the emissive particles are on the surface and the magnetic particles on the inside. And so you see this beautiful order happening. When you have particles that are really all the same size, really like atoms, when you put them together, they can order in really interesting ways. And you can see the chemical analysis on the bottom. The first application happened in the late 1990s in biomedical imaging, cell labeling. And there was a company that was created to commercialize that, and they did an amazing, really pioneer work on that. And you can see here a cell labeled with quantum dots in the nucleus and dyes on the outside, and the dye bleaching out and disappearing as the quantum dots survived because they're little pieces of rock. We did a bunch of in vivo experiments and showed that by choosing the surface ligands correctly, then we were able to make these things biocompatible. So in green here, you have the vessels in this image here, and then we inject quantum dots, and you can see them sort of getting out of vessels into the tissue without aggregating. And so this then has led to a whole bunch of studies of using the quantum dots to understand the tumor microenvironment, for instance. This is an image of using quantum dots to double label cells in vivo. These are hematopoietic precursor cells using intravital 2-photon microscopy, and you take two colors, red and green, and only those cells have receptors on their surface that can bind to these two colors, and the final color is blue, which labels the nucleus of normal cells, but not those of those basically stem cells. And so now when you go with a microscope and you look for yellow, which is the combination of red and green, you see this one cell here, which is the cell that you're trying to study, and you want to study its microenvironment to see how it survives in the bone marrow, in this case here. Color downshifting. This is basically what color downshifting is in the previous slide. It's taking the blue color and creating new colors out of it. And this is the big application. There were two companies that were pioneers in this, Nanosys and QD Vision. The first commercial product was using LED light, and which at the time was too blue, and incorporating a little bit more red in it, using a quantum dot film on top. That came out in 2010. It's a little too complicated for a light bulb, which doesn't cost too much money. So that turns out not to be a great commercial success. But people are still working in that area to make the color of LEDs more acceptable. But the application that turned out to have legs is in displays. Because the gallium nitride blue diodes were invented and were being used to create the light in displays. The first television was a Sony television based on cadmium selenide. Then Samsung introduced indium phosphide quantum dots, and now a lot of these displays, which they call QLED, are based on using gallium nitride blue emissive diodes, and then green and red LEDs, quantum dots to create the panoply. It gives you displays that are less energy intensive with better colors. I'm going to skip this last slide, this last application, and go directly to my concluding remarks here. So at the beginning, we were interested in quantum dots of semiconductors. The process that we invented, that Chris Murray invented along with David Norris in my lab, can be applied to many other materials. It can be applied to metals, semi-metals, magnetic materials, ferroelectrics, oxides, etc. The process of assembling these particles into these artificial solids, you can combine now all these materials together. And you can think then of what the future could be if you combine a magnetic material with a semiconductor and a metal material in an organized way, and combine those properties together and create new things. And that's what the excitement is. You know, we're creating new things. We're not quite sure where it's going to go, but we know that something interesting is going to come out. Over the course of the last 30 years, people, by adding different kinds of ligands, have figured out how to make spheres and cubes and rods and platelets, make them helical like DNA, chiral, handedness with handedness. These assemblies can also incorporate organic materials. So we have now a new world, this new nano-world of material, which we can try kind of really like a periodic table, which we can begin to assemble and see what new properties come out. The applications, I showed you light emission applications in displays in the biomedical area. Solar energy is another big one that people are working on. Catalysis and photocatalysis, this is where it started with Lou Bruce at Bell Labs. there's still a huge amount of work going on there and a lot of progress. And I think the future is bright in that area. Electronics, optics, quantum system, you name it. The field has grown exponentially. And the more people you have working there, really bright people, the more likely we are to come with applications that are going to change the way that we look the world around us, that we live, as the displays have. Now, funding is a really important part of the work that we do, and we wouldn't be able to do that without funding from both government sources, foundations, and private companies. It's not enough to have government funding. You need to have a mixture of both, of all three in this world. And finally, I want to thank especially the students that did this work. The students are the heroes here. They're the ones that actually are in the lab doing the work every day and accomplishing these miracles. And I thank you.